Swayam Prabha. Digital India. Educated India.
Welcome. In the last lecture, we started discussing what is known as a hydrodynamic interaction, and the motivation for doing this is we had earlier described the Rouse model, which qualitatively explains that the diffusivity will decrease as the number of segments increase in a chain, but the scaling law was not correct. So today we will take the discussion further. The discussion was on lines like what was missing in the Rouse model, and the missing part was these particular interactions I am talking about, and then using that we will develop what is known as the Zimm model. So until so far, what we have discussed in the hydrodynamic interactions is that if I have a system of particles, then the force that is acting on any particle is actually affecting other particles in the solution by the means of the fact that each of the other particle change the flow field around the particle. And then what we had established is the velocity of particle n or bead n must be related to the force acting on other particles in solution by what we refer to as the mobility matrix. And as we discussed, in a well dilute case, we recover what we had for the Brownian motion of free particle, but that is really very low concentrations. Otherwise, we have to really solve for the effects of hydrodynamic interactions. So the approach we are going to follow, as we already hinted, is we are using the Stokes approximation or low Reynolds number hydrodynamics that essentially is based on two key ideas. The first idea is that we assume that the fluid is incompressible, and for that we have the continuity equation del dot V is equal to 0, or in Einstein notation we have dou by dou R alpha V alpha is equal to 0. The second assumption is we assume that the inertial forces are small. That is anyway true for low Reynolds number. It turns out that we have a factor of Re coming in front of the prefactor of one of the equation, and we can drop that term if the Reynolds number is small, and that term is our inertial term. So in that case, we can write the expression for the force acting in terms of what is known as the stress tensor. So, del is my stress tensor and G is my external force, which again in Einstein notation is something of this sort. Okay. Now, for the stress tensor sigma, we use what is known as a constitutive equation that is true for a class of materials. So, if I have say a Newtonian liquid, later on in our lectures we will go in details of the continuum mechanics, and then I will talk in more details about what the constitutive equations really mean. But at this point, you can recall from your transport phenomena class, if you had, that the stress tensor is given like this for a Newtonian liquid, where this is the solution or solvent viscosity. So, now to approximate the external force, we will use the idea that the external force is because of the other beads that are present in the solution, and every bead correspond to a force say Fm, then the net external force should be sum over Fm multiplied by R minus Rm, okay, where Rm is a position of mth bead and the sum is over all values of m. Okay. We have used this kind of an idea before in our treatment of excluded volume. Essentially, the idea is that at any location R, we will look at how many beads are present, and then for those many beads we will simply add up the values of force acting on the bead. Okay. So, of course, this kind of a treatment makes an assumption that we really have a point particle with size 0, because we are using a delta function, but nonetheless it gives us a good approximation of the mobility matrix. So, we will essentially use that term here. So, if I now use this expression, what I then get is the equation of motion as the following. So, we can solve this particular equation by the technique of Fourier transform. I will not really go in the detailed derivation, but I will put the final results here. If I solve by Fourier transform, what I do get is my V of R is sum over for all values of n not equal to m, some function r minus r n dotted with f n, and this is what we have for mth particle, okay, where this function h, I want to differentiate that with the mobility matrix by noting that this is a function that we get by making an approximation, that is the Stokes approximation. So, this h is referred as the Oseen tensor, which is given by the relation 1 by 8 pi eta s r, the identity matrix plus r cap, where r cap is a unit vector parallel to r. Okay. Of course, this is equal to infinity at r equal to 0, because the denominator has an r in there. Okay. Now, this is a flow field that is being generated, and of course, the particles are moving in the flow field. We will make one more assumption here, and the assumption is that the motion of the beads at a particular point is same as the flow field that is prevalent at that particular point. So, we are going to assume that the motion of, say, nth bead is the velocity that exists at the position of the nth bead, which then is a sum over the h r m minus r n. H is the Oseen tensor here, and dotted with f m, and then this Oseen tensor is now the mobility matrix we have defined in the very beginning. Okay. So, there are certain assumptions that we have made here. We have made the Stokes approximation that allows us to solve the flow field expression, and for that I have got an expression in terms of what I call the Oseen tensor. Then I make one more approximation that the flow field basically also provides the expression of velocity of the bead, that is, the beads are also moving by the same velocity as the existing flow field at that point. And using these two ideas, I have established that the mobility matrix is essentially given by the Oseen tensor. Okay. The only trick here is that at r equal to 0, this is basically infinity, right. So, we must, and the reason why this issue happened is because we have treated the particles as being point particles. We did not account for the size of those particles. Okay. So, if I account for the size, we can of course derive the expression, and in that case we will not have this kind of a problem. But there is a approximate yet workable solution to this, and that solution is that for m equal to n, we will assume that the mobility matrix is simply I by zeta, or this can use the diagonal terms of the mobility matrix. Of course, we have to define a mobility matrix for every pair of n and m. Okay. So, with these ideas, I can then write the expression for the Brownian motion or the Langevin equation for, let me use the word, interacting Brownian particles, just to differentiate from the free particle case. So, now it is, we do have the similar form, but with a mobility matrix appear in our equation. So, earlier, just to recall, we had an equation that was like and now the equation is modified because we are considering the interactions between various particles, or considering the fact that the force acting on any particles affects the motion of all the other particles in the system. Earlier it was like the force acting only on that particle affects its motion. Okay. So, now if I consider the case of an ideal chain, that is no excluded volume, which by the way correspond to what we referred as a theta solvent condition. You see, like now I am becoming more discrete in our representation. We are differentiating between the theta solvent and other solvents, and the reason is like this is what will give us the correct scaling laws, in addition to accounting for the interactions that we have discussed. So, then in that case, just to recall from our previous discussion, any bead in the system is experiencing the spring force due to the m+1th bead and m-1th bead, the bead after this or bead before this. And if I had the spring constant k, then the force acting on that bead, or the energy due to these two spring interactions, is given as something like that. And so we can write dou u by dou rm with a minus sign as minus k rm minus rm plus 1 minus k rm minus rm minus 1, which is minus plus k rm plus 1 plus rm minus 1 minus 2 rm, which we had approximated as k dou 2 r by dou m squared. Okay, and that is how we take it to the continuous space. The rm now become r as a function of m and time. Okay, so we use the same idea here, and then we have the expression that is what correspond to a Zimm model in theta solvent. Okay. So, now we can solve the equation that we have derived. Again, the solution becomes somewhat tedious. So, I will only take you through the main points in the derivation and explain you the key results that we make or the key assumptions that we make in the scheme. So, we start from the point that the mobility matrix is given by the Oseen tensor. So, now R is the distance between n and m bead. So, I call it R vector n m absolute value. So, this entire thing is the R that I had multiplied by I plus and that is for n not equal to m. This is what we had discussed earlier, and then for n equal to m case I use the expression I by zeta. Okay, to proceed, what we do here is you keep in mind that there are many beads. So, every bead is interacting with many other beads in the solution. So, of course, we have to solve for many mobility tensors or mobility matrices. We make an approximation here that is called the pre-averaging approximation, which goes like this. The pre-averaging approximation, that is, I will approximate the mobility matrix H and M as the integral over the R n values, the set of values representing positions of each of the beads in the system, multiplied by the H and M multiplied by the probability to get that particular distribution, and of course, we are going to use the equilibrium Gaussian distribution that we have derived. And then this quantity is assumed to be equal to the pre-averaged H and M, and that is given by simply the pre-averaged versions So, I am really skipping the key points, many points in the derivation, and only illustrate the key points up there. This happens to be I by 3, the ensemble average of that, and so I have so I am simply replacing R and M by R n minus R m. Okay. So, we have replaced the mobility matrix that is appearing first by the Oseen tensor, but then we noted that we have to compute many of these tensors. So, we use the pre-averaged version of this, and by the pre-averaging we have got this, and then we use the fact that the distribution of the bead positions are given by the Gaussian distribution. So, I will use the fact that the P is a Gaussian function, and if I do that, essentially what do I get is so I put my expression for the Gaussian distribution that I have derived early in the course. For 3 dimensions, and we had the pre-averaged value of the mobility tensor, that is this expression, and this on solution gives me something like so if you look at this expression that we have got, so this is some function of n minus m multiplied by the identity matrix I. So, using this particular expression, what I can then get so we had this expression. So, now I have so we use the identity matrix that basically gets rid of the dot from the expression, and then we had this entire thing. Okay. So, just to give you a brief review of what we have done so far, we started with the Langevin equation for the interacting Brownian particle. It is different from the free particle case in the sense that the force acting on the particle also affects other particles in the system. Then we have been looking at this for the ideal chain case, where the only force acting on the bead is the spring force due to the neighboring beads, that is the case of a polymer chain. And then we have made an approximation similar to what we had made earlier in the Rouse model, that we get a finite difference like form in the expression of the force, and then we think of the continuous analog of the discrete bead spring model. Using that, I get the expression that I have, and then we tried to solve the Zimm model, and I only hinted at the main steps in solution. So, we started from the Oseen tensor that we have derived by Stokes approximation. For the mobility matrix, we have used the pre-averaging approximation, that is, we approximate the mobility matrix by its average value that we get by integrating, keeping in mind the probability distribution of the beads in a polymer solution that is at equilibrium, that is given by the Gaussian distribution for an ideal chain, and using that, after some mathematical manipulation, I have got a function of n minus m, that is a function of the distance along the contour multiplied by the identity matrix. So, this is basically a diagonal matrix that we have got. Mobility matrix may have contained an off diagonal term, but since we have averaged it, we get a diagonal matrix, and if I plug that in back in here, we do get the expression that you can see in the towards the end, and I want to start from this particular point in the next lecture. Thank you.